background, and I'll pass it over to your good selves. Thank you very much.
Okay, thank you, Sam. So welcome to our presentation on robots to automate farming with Sam Turnnidge and Martin Stace. I'd like to say thank you to the IET for hosting this event for us, and thank you to Sam Wayne for organising it. So you might be asking the question, well, who is Earthrover? So at Earthrover, we develop field robotic solutions for vegetable and salad producers so they can improve their production. Our current solutions reduce the producers' reliance on chemical application and provide them with a detailed insight on their crop in order to sell more and waste less. My name's Sam Turnnidge. I'm the Precision Agriculture Field Engineer at Earthrover. A little bit about me: I graduated from Harper Adams University in 2019 with a degree in agricultural engineering, and from a young age I've experience in agriculture in both arable and livestock, but at the moment I specialise in agricultural technologies and agricultural engineering. I'm joined by Martin Stace, who's the principal engineer at Earthrover. He has 30 years of experience in a range of different industries, and he's currently leading the design of the vegetable harvesting systems at Earthrover. So yeah, let's start. So what is agricultural robotics? Well, there currently isn't a formal definition for the term agricultural robot or agrobot, and there isn't really an official recognition for the function of robots that perform agricultural tasks. However, there are unofficial definitions that have been proposed, and my favourite definition being the following: a mobile autonomous decision-making mechatronic device that accomplishes arable and livestock tasks under human supervision, but without the need for human direct labour. And from being involved in the industry from a young age, agricultural technologies are becoming more and more prevalent in the industry. And I believe that agricultural robotics are a part of a new technical revolution that's going to bring new companies and exciting innovations that will greatly benefit all aspects of farming. So yeah, thank you for sticking around, and I'm going to pass it over to Martin, who's going to talk about the current situation in agriculture.
Waiting for the screen to come up. Right. In this first part of the presentation, we thought it'd be a very good idea to actually go through what the current situation is in agriculture. Only really, until you actually understand what's actually happening right now in agriculture, can you really start to look at how you can improve agriculture for the future. So first of all, I'd like to talk about the current situation. So current world population is 7.67 billion people. This is expected to reach 9.8 billion by the year 2050. And currently, certainly in the West, we've actually reached saturation in agricultural food production, the land usage. And this is certainly starting to happen in the third world as well, in the developing world. And you're now starting to see areas that really shouldn't be used for food production starting to be used, such as the rainforest in South America. So we're actually seeing quite a lot of stress on the land, right? More and more being turned over to farm usage. But it's not just the world population driving the need for more food. The world is changing a lot. And in the next few slides, I'd like to actually go through these sort of the environmental, the ethical, and the economic pressures which are on land usage around the world. So first of all, economic drivers. Food production costs increase every single year, but the increased cost and the value of that food is not increasing at the same rate. You can certainly see from this graph from America that the blue line shows the cost of production of food, but the red line showing the actual crop revenue is not tracking at the same rate. So you're seeing more and more cost for producing food, but the cost of actually the return on the production is not as great. So you're actually seeing more and more reduction in turnover for farms. On top of that, you've got the fact that farmers Farming is not seen as got a good image. People don't want to work on farms anymore. Labour costs are going up all the time. The minimum wage in this country is increasing all the time. And also you're now starting to see a lot of people not wanting to work in the countryside. You're seeing a lot of people moving from the countryside into urban environments. You see that a lot more in other countries as well. Certainly if you look at China, there's been a big push to take people from the countryside over the last 40 years and move them into the urban environment to work in manufacturing and not work on the land. So that means that production output, they want people to increase production output, but all these pressures are causing a lot of pressure on the economic production of food. So on top of that, there's a lot of ethical drivers pushing this. So agri-food is one of the largest manufacturing sectors in the UK. It generates 108 billion annually and exports 20 billion worth of food, of our manufactured goods. And also in this country, there's a large amount of uncertainty about the use of workers coming into this country. A lot of migrant workers come into this country every year, and Brexit is now putting a lot of pressure on that. The government wants to reduce the number of migrant workers, and that's not just this country either. If you look at California in America, you're now seeing the Americans putting an awful lot of pressure to stop migrant workers coming from Mexico to work on the land in California, and the labour rates in California are very high as well. So the minimum wage is going up, not just in this country, but all over the world. And on top of that, a lot of working on the land is a good job to have. People see it as there's no chance of promotion. It's hard manual labour. The picture on the right here is farm workers in Durham harvesting broccoli. It's some hard manual job, walking many miles a day. For very little pay. So it's not seen as a glamorous job in the slightest. And it's also seen as poor welfare. You know, you're walking across a field harvesting broccoli, you've got a 9-inch machete in your hand. It's you know, you can hurt yourself very easily. There's an awful lot of accidents in farming. So it's not an industry where people are seen as having is not a good comfortable. It's not sitting in an office enjoying yourself. It's working hard on the land. Not everybody enjoys that, and it's certainly not an area where people want to go into it. So the next area towards there's environmental drivers as well. So as we said before, is it increasing as the population of the world increases? We need more and more food, and instead of making better use of the land, all we're doing at the moment is increasing the use of land usage around the world by chopping down forests to produce land to put cattle on or grow palm oil. This increases energy consumption. Larger and larger machines in developing worlds are being used for agriculture. This is pumping more and more pollution into the atmosphere. This increases use of land drainage, damaging the natural environment and wildlife. Certainly the rainforest, we're seeing the complete destruction of complete ecosystems in the rainforest. And also, as more and more land is used and we want more off the land, we're using more and more agricultural chemicals.
Martin,
can
I just interject a second? Any chance you can turn your microphone up a little bit? A few people have got difficulty hearing. So to turn up your microphone, if you just move your cursor to where it says mute, and then you've got the little arrow to the right of it, and then you've got audio settings, and then you've got microphone, and then you just turn it right up, input level volume. Just if you can turn that, that would be great. Don't know if it.
Where do you say go? Sorry.
If you just move to where the mute is at the bottom left-hand corner, and then you've got a little arrow to the right of it, click on that, and then you've got audio, and then you've got microphone. It says test mic, and you can either automatically adjust microphone volume, or you can, if you click that off, and then you can actually move it up. So I don't know if I'm a bit louder now because I've just dragged it off to the right. Does that make sense? So you untick automatic.
So microphone.
Yeah, so you got audio and then untick where it says automatically adjust microphone volume. So make sure that's unchecked and then you can turn your volume right up.
All I've got is audio settings.
Yeah, so you've got audio, then you've got speakers.
Right, I've turned it all the way up now. Can you hear me better?
Yes, loads better.
All right, sorry about that. Okay,
Interject.
sorry, that took a bit. It wasn't the same as yours, I'm afraid. Okay, so
Right.
I'll start to get on the environment drivers. So as the world's population increases, more and more land use for agricultural industry. And this is putting more and more pressure on the world. It's increasing the deforestation, certainly in South America with cutting down of rainforests. This is damaging the environment. It's destroying complete ecosystems and wildlife. And on top of that, as we use more and more land for agriculture, more and more chemicals are being spread on the land, which is doing even more damage. And then on top of that, in the developing world, there are more and more large machinery is being used, which is damaging the land again and increasing pollution to the atmosphere. So certainly, as we see more land usage, we're seeing more damage to the environment, and we're not actually seeing any increase in the percentage of food production per hectare. So move on to soil and agrochemicals. So the current intensive farming methods degrade the soil quality, and it breaks the soil structure down. Continuous ploughing of the soil, disturbance, continually tilling the soil to remove weeds, degrades the soil quality. Certainly in the 1930s, we saw the Dust Bowl, and that was caused by poor soil management. Controlling the levels of fertilizers with the current application of fertilizers, large spraying machines, is very difficult. We can't easily control the amount of fertilizers and pesticides in the soil, and you see varying degrees in poor nitrate control in the soil. And then on top of that, spraying large scale, it's very difficult to control the spread of these agrochemicals across the land. And then again, bigger and bigger machinery increases soil compaction. Soil compaction means that when it rains, instead of the chemicals going into the soil, they just drain off, and you see pollution happening into the waterways from soil, from the agrochemicals rolling off the land. So again, the current methods in farming do not do the soil that much good, and you're seeing breakdown, and that reduces the output of farming land for a whole range of different soils. So again, this is a large area of water. The agriculture uses 70% of the fresh water used in the world. So if you look at all this of the industry, domestic usage, 78% of that is actually used for producing food. And this is very damaging to the planet. We use large amounts of water out of waterways, and it's very costly to the production of food. And we need greater efficiency in putting water in the right places on the land. And that's certainly an area that Sam's going to talk about in a minute, about how robotics can help with water usage. So I'm going to pass on to Sam now, who's going to talk more about how robotics can help solve these problems. Let's stop sharing.
Okay, thank you, Martin. Okay, so let's look at the current involvement of robotics in agriculture. The first commercially available robots in arable farming cover three main tasks, and these include eliminating weeds, monitoring crop performance, and harvesting specialized crops. In livestock production, robots are currently used for cleaning, animal monitoring, and feeding. These exciting developments are being made to expand the use of robots in agriculture. So in this section, we're going to go through the current uses of robots, explaining their benefits in the system, And then at the end of the presentation, I'll discuss what the future might look like for agriculture. So let's start with the first operation, which is normally done in arable farming, which is soil preparation. Cultivation is currently used throughout the globe in both developed and developing countries. The principles for cultivation is to turn the soil into a fine tilth, which provides an ideal environment for seeds to germinate. Cultivations are typically split into two groups, which are primary and secondary cultivations. Primary cultivations include ploughing and subsoiling. And if you're unaware, subsoiling is a deep cultivation technique where the aim is to target compacted areas under the surface of the soil, and these are typically called hard pans. Ploughing lifts and inverts the top 8 to 12 inches of the soil, bringing fresh nutrients to the surface and burying the stubble from the previous cropping to decay into valuable organic matter. Secondary cultivations include power harrowing and rolling, which focuses on the top level of the soil profile. Cultivations are typically slow operations, and they can often take several days to complete, subject to correct weather conditions. Heavy farm machinery will struggle to operate and produce a suitable environment for seed germination in wet and difficult conditions. For primary cultivations, costly high horsepower equipment is needed to pull subsoilers and plows through deep through the soil. Cultivations are costly in terms of inputs. Typical cultivations tend to use between 12 to 15 litres a hectare of fuel. Farmers typically spend more money of fuel during any part of the season. Current projects that involve robotics for cultivation operations have retrofitted autonomous equipment onto current farm vehicles and have seen benefits in productivity as the machine can run for longer hours, covering more land and operating 24 hours a day. Developments are underway to utilize hybrid engines. By using both diesel and electric, the carbon footprint is reduced, and so are the fuel costs. In the future, when electrification has matured, there is a possibility of fully battery-powered robots that can perform cultivations with a zero carbon footprint. Also, the possibility of lightweight robots would increase the opportunity or the window of opportunity for necessary cultivations. For example, lighter machinery could operate in conditions and environments where larger machines cannot. Having this larger operating window will improve farm productivity and reduce the risk of rushed operations to meet tight deadlines. So moving on from soil operation, we can talk about planting. Most arable crops are planted using a planting implement, which is mounted at the rear of the tractor. However, in less developed countries, seeds are broadcasted onto the surface of the soil with a spreader. These seeds are then cultivated into the ground so they can be buried, and then the ground is typically rolled to have an adequate soil and seed contact for good crop establishment. Vegetable and salad plants such as lettuce, cabbage, and broccoli are transplanted into the soil. A planter that covers 3 beds or 9 rows of plants requires 9 workers at the rear of the implement to feed the plants manually into the machine. A bit like cultivating, really, planting can be slow and sometimes require high fuel usages. Depending on the soil types, the planter may need to run a bit deeper, causing the tractor to slow and burn more fuel per hectare. Transplanter workers manually load the trays of plants into the machine at the end of each double pass of the field, and this alone can take 5 to 10 minutes each time. However, fuel usage is not the only high cost that a farmer must pay. Multiple transplanter workers are not cheap, and the total cost for planting can be extremely high, especially when running multiple planters. With a partly human operated machine like a transplanter, human error can occur. For example, if a plant is not fed into a machine correctly, the plant may not be sufficiently planted in the soil. Human error can also cause variable plant spacings. Similar to the developments in cultivation robots, current autonomous planting systems use autonomous equipment that is retrofitted to farm machinery. However, in the future, robots with self-loading capabilities will be able to run throughout the night and day, not being subjected to the physical and legal limitations of that of humans. Robotic planters could also adopt precision planting capabilities that we see today. For example, robots can store agronomic information in its software and in the form of prescription maps, which could allow the robot to vary the rate of seed per hectare, depending on factors such as soil type, soil pH, drainage, and soil nutrients levels. Robots could also record the plants that have been planted in real time, allowing the farmer to know exactly what's going on in the field. Robotic planters would take up the role of 9 to 12 workers in one operation, reducing the manual labour costs considerably for the farmer. And this next slide shows me, I visited a organic broccoli farm in the UK, and you can see here on the right the transplanter, and this is a 3-bed transplanter, as I mentioned in the slide, and you can see the 9 workers working on the machine, and the 1 worker that's working behind the machine to check that all the plants are correctly planted in the soil. On the right here, you can see the trays of this was broccoli. That's loaded on the machine manually, as you can see here in front of the workers. So moving on, we can look at crop monitoring, and the question is how do you walk thousands of acres of crop every week? And the answer is it's not possible for humans to walk through this amount of crop and record detailed information. The issue is that you cannot manage what you cannot measure. The current way of crop monitoring is not sufficient to maintain a high level of crop performance. Farmers need this accurate plant-by-plant data for yield and early detection of weeds, pests, and diseases. If you do not have this precise data on plant information, you risk application of costly inputs like pesticides, irrigation, and fertilizer. In addition to this, without detailed plant information, you may risk inefficiently using costly labour forces for tasks such as weeding and harvesting. Alternatively, you may be too late to act upon damaging issues such as an infestation of weeds, pests, and diseases. So there's 4 different stages to robotic crop monitoring. The first stage being that sensors monitor the crop to generate data captured by the robotic platform. This data is then processed by specific software and artificial intelligence. And then the farmer is presented with intervention options. And then finally, the farmer can decide based on these options how to act accordingly. So there's currently several robots in development and commercially available that autonomously detect and record plant information. Crop monitoring robots are lightweight machines which prevents disturbing the soil and maintains soil structure and reduces soil compaction. Several crop monitoring robots are also fully run on battery power, reducing the carbon emissions of the entire farming process. Benefits of crop monitoring robots is that with crop counting capabilities, farmers can compare the number of plants planted in a field, so the number that they've planned in their planting forecasts. The plant size and information, farmers can see if their crops are thriving and can analyse the history of plant growth from previous weekly scouting sessions. With weed pressure detection, allows for farmers to view problematic areas and act accordingly. And with crop forecasting capabilities, farmers can plan when fields or plots can be harvested. In the case of high value vegetable crops like broccoli, where plants are selectively harvested based on market requirements, farmers can use data visualization software to see the number of plants that are ready to be harvested. Having this data reduces the risk of missing harvesting ripe produce and increasing crop yield. So one thing that you might not know about Earthrover is that we have our own autonomous scouting robot platform. The Earthrover pointer is a lightweight machine with a total mass of 75 kilograms. So we're really reducing soil compaction to a minimum and maintaining good soil structure and reducing soil erosion. The pointer is currently being used in the UK on a large organic vegetable farm throughout the growing season, and it's also being used on our test farm in Barcelona. The system provides the farmer with accurate data with its onboard RGB depth camera and extensive neural network for detecting, sizing, and mapping plants in real time at a rate of 2,000 plants a minute. With the aid of RTK technology, receiving correction messages through radio and N-trip and having our own base station means that plants can be mapped to an accuracy of plus or minus 10 millimeters, and robots follow an exact path during each scouting session, minimizing soil disturbance and machinery traffic in the field. This is a screenshot from our data visualization software, which provides detailed information on plant density per hectare, plot information, and plant sizing. Through our software, the end user can locate problematic areas and obtain its GPS position, meaning that the farmer can locate the area of interest in the field. As you can see at the bottom here, the ER pointer also generates and stores images at a rate of 1 image per second. And all these images are stored in our data warehouse. So if a farmer is away from the farm and notices an issue with the field from our maps, he can view these images for confirmation and make decisions remotely. Each individual plant that you see here on the map has its own ID number, so we can analyze and know each plant throughout its life. With our data, farmers can model and forecast crops like never before. So from crop monitoring, we can move on to weeding. Weeds can be controlled in several ways, really. This can be through application of agrochemicals, mechanical weeding, flame weeding, or hand weeding, which is typically done on organic farms. Agrochemicals are applied with expensive spraying machinery. In less developed countries, agrochemicals are still being used. However, farmers are typically not following the correct health and safety guidelines, which can pose risks to the operator. Farm workers can be exposed to harmful chemicals through inhalation, skin absorption, and ingestion. And this significant exposure can lead to long-term health effects, such as an increased risk in some cancers. There's issues with birth defects, disease of the lungs, liver, and kidneys, and also some nervous system disorders. Heavy farm machinery increases the level of field traffic and increases soil compaction, which damages soil structure for plant growth and development. Workers need to be trained on how to identify weeds, and if training is inadequate, then workers may damage these high-value crops. Farmers, particularly in the high-value vegetable industry, spend large amounts of money on manual labour hand weeding. Typical cost for hand weeding are around £400 to £500 per hectare. And if you really think about that, fields that contain tens, if not hundreds, of hectares of crop, these costs can really add up for the farmer. Hand weeding is a slow process as well, which is seen as unappealing to many people as it's repetitive and physically demanding. Therefore, limited worker availability is a common problem, not just in the UK, but globally. Currently, there are several robots that are currently in development that are equipped with modern technologies that can detect and deal with weeds. An example pictured on the bottom right here is the mechanical weeding robot from Neo Technologies. Benefits from using robots for weeding, eliminating the need for harmful chemicals, reducing environmental damages, and improve worker health and safety. They also reduce the need for costly manual labour and provide reassurance as a solution for when hand weeders are unavailable. They also provide capability to work in unison with other robotic platforms. For example, crop monitoring robots could provide fields and specific locations where there are large densities of weeds that are damaging plant growth. Earthrover is actually focusing on this area of agriculture, and we have developed our own light weeding robot called the Earthrover Terrier, which is currently in its development and testing stage. Our patent pending light concentrated technology has been tested in a laboratory environment during 2020, but is now being tested on farms in Barcelona. The unit itself works at a wavelength that's optimized for plant leaf absorption, using a dedicated camera system and an embedded computer to detect weeds using its AI and control system. The Terrier robot is fully battery powered, and therefore it is a carbon emission-free solution without disturbing the soil, retaining soil carbon content and keeping good soil structure. The Terrier works on a start-stop system, meaning that the robot will continue autonomously down the field until weeds are detected, where the machine will stop and deal with the weeds. And I'd like to show you some pictures that were taken from our testing over in Barcelona. So over here on the left is where we're going to be testing on the weeds, and over on the right here is our control area. So this is the picture taken before weeding, and then I'll go to this is the picture after weeding. So on the left here you can see a significant reduction in the number of weeds in the area. If I go back, you can see the weeds, and then the weeds are no longer there, and you can see, if you look closely, evidence of where the light concentrated system has been applied. So if we move to 12 days later, and during those 12 days, they had considerable amount of rain and sunshine, so it was optimum growing conditions for weeds. And as you can see in this area here, there are new weeds that have developed. And then after this picture had taken, we applied another weeding session, and here you can see 22 days later, where there's evidence of little to no weeds where we've been weeding, and in the control area and surrounding area there's many weeds. So yeah, this is proof that using light concentrated technology can really benefit a producer in terms of weeding. So I think let's move on to harvesting. So despite the demand for more efficient production for the growing global population, millions of tons of fruits and vegetables are still handpicked every year in open fields and greenhouses, along with high labour costs for running hand pickers during the harvest season. The availability of skilled workforce that accepts repetitive tasks in sometimes harsh field environments impose uncertainties and sometimes timeliness costs. With the manual handling of fruit and vegetables, there can be also food safety concerns, and mishandled produce can reduce product quality and may prevent the product from being sold to the consumer. The question that is on everyone's lips really is, should high value produce still be handpicked in a time where technology is more advanced than ever? And several companies are looking into this and are developing and have developed selective harvesters for high value crop market, focusing on the harvesting of berries and peppers. As you can see on the bottom right here, we have a robotic strawberry picking robot called the agrobot, which works with multiple strawberry growing systems, and they're capable of autonomous navigation along crop rows, locating and picking ripe fruit, grading picked berries and placing them into punnets, as well as alleviating the growing difficulty of recruiting enough skilled picking labour. Other benefits provided by robotic picking solutions are even of more interest to customers. For example, they provide consistent picking performance throughout the working day. They can grade and control the quality of fruit in situ without the need for repeated handling. They can also operate during the night time, and particularly when temperatures are lower, which maximizes the shelf life of picked fruit. They can also gather data for precision crop management to optimize yields, quality, and marketing, and they can improve the interaction between humans, machines, and plants. So now on the next slide is a video of the agrobot. I'm going to play this video, but after this video, I think it'll be good to have a break, and maybe we can answer some questions. Maybe a 5-minute break, and then I can move on where I'll be talking about livestock production and the benefits of robotics in those systems. So I'll just stop sharing my screen as I need to change a few settings for this to work properly. Okay, so if we want to have a 5-minute break, grab a drink, and if you've got any questions, feel free to put them in the chat, and hopefully I can answer them for you. Thank you.
Brilliant. Thank you, Sam. Thank you, Martin. I'll let Sam and Martin grab a drink if they need a drink. So I'm pleased to say we've had quite a few questions on the Q&A. I will just read out a few of them. Let's start off with a fairly straightforward one. One question is, can you say a little bit about how you geoguard the robots? In other words, how do they know the limits of the field and don't go wandering off down the motorway or anything like that?
Yeah, that's a good question. So all our robots are controlled for our farm control system. They have their own robot path that they follow, and using visual odometry, they can recognize beds. So it's if they veer off the path, they will just stop. But yeah, with the aid of visual odometry, they can visualize the beds and maneuver down there. And with our RTK base station that we have on the site, it's fully controlled. So that's not much of an issue.
So just to expand some of those, I know what you're talking about, Sam, but RTK is a very accurate GPS, real-time kinematic. And what was the other one you mentioned? Visual odometry. Now, I'm assuming that means it's a camera looking down, and it's a bit like a child who's just looking down when they're walking along, and you get a bit of an idea of your flow just from looking at how things are moving, a visual flow. Is that right?
Exactly, yeah.
Okay. We've got a few questions about the weeding bit. So I know we've got to be careful here because you did mention that it was patent pending. So
exactly.
Yeah. So I'm not going to ask you to really answer any. There's quite a few people who are interested. How does it? Very interesting one. So I'm going to skip over those ones. But a question that is related to that, but it's nothing to do with the patents, is. It was interesting that you showed a picture 22 days later and it was still bare. But I was wondering, did you still have to use your patented weeding system leading up to those 22 days? Or did you last weed 22 days ago and nothing grew there for 22 days?
So it was two applications. There was the first application, and then 12 days later, we then did another application. And then it might have been confusing because it said 22 days later, but that was from the first application. So in fact, it was 10 days after that second application.
Okay, so you apply this system every 10 days. So in essence, what you could have is a robot, and I was glad to see that it was solar powered as well. So that's
yes, yeah.
So that will just go, and as long as it can cover a field in 10 days and carry on doing it's you'll have a completely weed-free field, which is
exactly,
fantastic. So another question is, can you tell us a bit more about the decision-making process used by the weeding robot? So can it recognize weed seedlings from crop plants, for example?
Exactly, so the way we do that is through our plant imaging, so and through our neural network. So we train the system to tell it what's a high value crop and what's a weed. And we did this in our laboratory environment. We grew plants indoors, and we took as many pictures as we could, and then from that we could train the system accordingly. And so during the when it's operating, it can tell the difference between a weed and a crop. And it's the same with our scouting system. It uses similar technology. It can tell you what's a broccoli plant, or what's a cabbage plant, or a cauliflower plant.
Excellent. Okay.
So,
and when it kills the weeds, it doesn't get rid of them. I presume that they're left to just break back down organically into the ground.
Yeah, exactly. Yeah. So once they're killed, they break down and turn into organic matter, really, which is which is ideal and helps plant growth and development.
Okay, because that was part of another question. So we had quite a few questions on the weeding. That's obviously a hot topic with everyone, certainly this time of year when everyone all the weeds that they've got in the gardens.
I wish I could have it in my garden.
Oh, yeah, perhaps we could try this out. Does the adoption of robots and the space required lead to a effective reduction in the ground? So do you get better yields, do you think, by using the robots? You get a more efficient use of the ground area?
It's a good question. Yeah, I think you do get a more efficient use of the ground that you're currently got. I haven't seen any farmers reduce the amount of land that they've that they're using with robots, but no, I think they improve production to a point where they could be it could be an option to reduce the amount of land that they have.
I think.
What? Sorry, go ahead, Martin.
One of the things I think, maybe not the weeding side of it, but certainly the scouting side of robotics, that is improving the yield off the land. Because if you can identify areas of the crop which are not developing because they're not being fed enough water, or you've got areas of the crop where they're being fed too much water, you can then target those areas. You can also target areas where we've got pests on them. So therefore, the whole crop comes to fruition, rather than you see some fields where there's a big patch in the field where nothing's actually come to harvest. And that's probably because the farmer's not been able to target that part of the field because he's not had the data to say what's going on with his crop. Certainly with monitoring systems, you've got that data real time all the time. You don't have to wander across thousands of acres. So the farm we work with is actually quite small compared to farms in the States where there's absolutely no way you could ever walk across the entire crop and look at what's going on. So if something goes wrong with it, it's probably gone wrong before you got anything, so you can do anything about it. So robots will definitely help with increasing yields on crops. And
does the system use some sort of neural networks as well? If you're allowed to say that, just say no if you're not allowed to say that.
There's a dashboard, that's what I can say, which tells you what's going on.
Okay, yeah. And other questions are, can it detect people and animals? And if so, can it stop? And how does it detect people and animals?
Yeah, sure. So similar to the tracking of beds, we use visual odometry although it wasn't shown on the picture on the slide, we will be implementing surrounding cameras that can detect people and animals, and we'll have a safe working distance. So once that object, whether it be a human or an animal or whatever, comes within that working distance, then the robot will stop. So it does have the ability.
Okay, thank you. Okay, so I don't know if you guys are ready to continue.
Yeah, sure. Yeah, no problem.
All right, for a minute. Yeah, okay. Or I can always talk for a few seconds longer. I will just give you a couple of minutes. So just for everyone watching, I've put some things up in the chat. The survey, for example, and also the location of our CPD certificates. And someone else has very kindly put the exact location of the CPD certificate link. So do scroll around and see if you can find that if you need it. It just has the title of the event on, and it's blank for your name. So just download it and put your own name on it, and that's for your portfolio. I've also put a link there for our website. So do have a look, and you'll find everything from our website under the files section, future events, etc. If you need anything else, do put it in the chat. If I can help you in any way, just ask, and I will continue to monitor the questions. Unfortunately, I can't ask all the questions, but I will do my best, and we'll have to just see how we get on for time. And as I mentioned, this will be available on YouTube, usually around about a week after the event, and there is a link to the YouTube channel there again. Okay, are you all good to go again?
Yeah, just start sharing my screen again.
Here then, thank you. Over to you guys.
Okay, so now in this section, we're going to be talking about livestock. And like I said before the break, the robotic uses in livestock. Just like arable farmers, really, livestock farmers can benefit from the use of robotics in their daily operations. The need for increased livestock production is pressing, and the use of robots can contribute to making positive changes in this industry. So a bit like crop monitoring, livestock monitoring is an important daily task, which should include inspecting each animal to see how they are performing compared to expectations and market demands. Without data, a farmer cannot make decisions effectively. Animal monitoring is typically done during each day. However, it's a slow process, and if the workers need to meet tight deadlines and other tasks, then animals may only be monitored briefly. By doing this, individual animals that are not performing as expected or are ill may be missed out and not correctly dealt with. In some cases, actually, this can lead to the animal dying unexpectedly or having to be culled. Losing animals is always going to have a costly effect on the farmer. And as the animals have utilised costly inputs such as feed, water, and bedding, while providing no real income to the farmer. Monitoring livestock can also be a dangerous process, and if not done by someone with sufficient experience, if they're not able to predict animal movement and behaviour while in the field or the barn, then there's a possibility for the worker to be injured. Going on to poultry farming. Poultry farming in the United States has become a growing industry over the past 20 years. Typical farms in the US hold hundreds of thousands of birds. Therefore, it's difficult and time-consuming for farmers to track animal progress at this sort of scale. One robot that's helping poultry farmers in the United States is the Chicken Boy. The animal monitoring robot uses several cameras to collect valuable data, which is then presented to the farmer in the form of detailed maps and graphs. Advantages of using this sort of system it includes higher productivity with accurate data on climate and early detection of diseases, faster detection of technical issues, improved animal health, lower animal mortality rate, and faster reactions to issues that are found. This information can also be shared with professionals like vets and nutritionists, which can improve the value of their services to the producer. So moving on from livestock monitoring, we can talk about livestock feeding. So in most intensive livestock production systems, more and more farmers are looking to maximize their animal performance through specific diets. These diets in agriculture are known as TMRs, or total mixed rations. So a TMR typically consists of a range of feedstuff, which includes quality forage such as silage or haylage, grains and proteins, but also vitamins and minerals. An important part of feeding livestock is the dry matter intake. The dry matter intake is the intake that the animal must consume, which contains required energy concentration for that specific animal in its stage of life, and also to achieve maximum animal production, a TMR must be precisely mixed so that food contains the correct percentages of feed. This process takes time and resources, with traditional feed mixes being done as a 1 or 2 person operation with a tractor, feeding wagon, and a telehandler. Depending on the size of the production system, multiple runs to fill the existing mixing wagon may need to be done in order to feed every shed. With this process being predominantly human controlled, human error can sometimes occur. Human error during the mixing process could lead to too much of one feed being used in the ration, which will not utilize animal performance. Costly feeding may also be wasted through mishandling. Autonomous feeding robots have been in the industry for the past few years, and further developments are being made. For example, robots such as the Aranom are becoming increasingly popular for livestock feeding. The feeding system is battery powered, therefore contributing to a zero emission production system and reducing carbon emissions. The benefit of this machine is that it automatically and precisely mixes feed to the correct level, so really optimizing animal performance in the system. The aeronom can be programmed to start feeding at specific times and can travel between sheds, providing the correct group of animals with the right diet. Minimal human intervention is required, meaning that workers can focus on other important tasks around the farm. However, in the UK, 85% of livestock systems are actually extensive, which means they're based outdoors. However, this doesn't limit the possibility of automation and robotics. Robots are currently in development that analyze grassland and sward height so that the farmer can optimize grazing opportunities and reduce the usage of alternative costly feeding methods. So let's move on to another stage, such as milking. So there are predominantly two types of milking systems that are used in the dairy industry. These are the herringbone and rotary milking parlours. The number of rotary milking parlours has actually increased in countries such as New Zealand and the UK. This type of system is typically dependent on the size of the herd. For herd sizes normally above 500, farmers normally opt for the rotary system. Traditional herringbone systems can be slow. For example, the loading and unloading of cattle takes time, and slower milking cows can hold up entire rows. Depending on the size of the parlour, milkers are constantly walking back and forth down the aisle, managing each cow. And really, for this system to work well, an efficient milking routine really needs to be put in place. Rotary parlours are also large, with lots of moving parts, which requires consistent maintenance, meaning that they are unable to fully inspect their cows while they're milking. With these systems, in some cases, udders can be damaged, and mastitis can be caused by mishandling of clusters. For example, they can get them dirty or excessive milking when the cow is dry. So robotic milking is becoming increasingly popular in livestock production. It's expected that by 2025 that actually 50% of all EU herds will be milked robotically. One commercially available robotic milker is the Lely Astronaut. The Astronaut uses a robotic arm which has provided itself as the smartest solution in taking care of the milking process. The robotic arm sits below the cow during the whole milking process and reacts fast to when teacups drop off to keep them clean. The arm follows the cow, allowing her to maximum freedom and movement while in the box. Increasing milk yields and cow health are the recognised and proven benefits of automating the milking process. With a robotic milking system, the cows are more relaxed, healthier, and therefore reward you with more milk. This is because the system fits much better with cows' needs and frees up farmers' times to give you true attention to cows. The Lely Astronaut uses hybrid technology. The Lely Astronaut has managed to reduce energy consumptions by as much as 20% in some cases. This is because the robot arm is transferred to a pneumatic cylinder, and electrical drivers require very little power to move the arm. So let's have a look at cleaning and maintenance. So having a well-maintained environment reduces animal stress, improves animal health, and then subsequently improves animal performance. In poultry sheds, diseases can have a serious effect on production. Due to indoor systems containing thousands of birds in a single shed, disease can actually spread very rapidly. It's still a frustrating fact that mastitis, reduced fertility, and foot health issues still count as the three main reasons for culling on dairy farms. Current practices for cleaning livestock sheds are often slow and arduous, as it's often that animals need to be moved into holding pens before the area can be cleaned. The current use of tractors and loaders means that in some tighter areas in the sheds cannot be cleaned as they're out of reach. These are either cleaned manually, which is slow, or often left behind, which could be a catalyst for disease spread. The scraping of slurry in indoor cattle sheds is usually done into a slurry pit or lagoon, which is a considerably dangerous task. slurry pits and lagoons are the main causes of human death in livestock units, unfortunately. Pits and lagoons act as almost like a fizzy drinks bottle, because as soon as they're agitated, gases are released. And these gases can be found in, and the gases that can be found in these pits and lagoons contain methane, carbon monoxide, ammonia, and hydrogen sulfide. High levels of hydrogen sulfide is particularly dangerous as it cannot be detected by the human nose, and fatal exposure can happen very quickly and without warning. Current robots that maintain animal welfare standards include the Lely Discovery and Octopus Scarifier. You can see these two here, the top being the Octopus and the bottom being the Lely system. The Octopus Scarifier robot turns and aerates the bedding in poultry sheds, which prevents the onset of disease and breast injuries, which can kill or seriously affect bird growth and development. The Lely Discovery slurry collector cleans the barn, keeps cows' feet, legs, and udders and tails cleaner, and helps inhibit the growth of bacteria. This reduces hygiene-related feet and other health issues. By collecting and disposing of slurry autonomously, this increases health and safety on the farm by keeping workers away from these dangerous areas. Both robots work with no human intervention and can be programmed to operate whenever it's necessary. By having this autonomous worker in production system means that valuable workers can focus on other tasks on the farm. These type of cleaning robots are small, meaning that areas within the sheds that can be cleaned and maintained effectively. So I think the next slide is a video of the Octopus Scarifier, which I'll show you now. So I'll have to stop sharing my screen and share again. So give me 2 seconds. Okay, hopefully this works. So as you can see here, you've got the or on the tablet had the visualization that the farmer could see, and the robots autonomously going up and down the soil, aerating the bedding, prevents fermentation of the bedding and reducing ammonia. So I'll just okay. So moving on from livestock, and we can have a look at pack houses, which contains both veg and the meat industry. In order to meet these growing demands, pack houses now need to think about optimizing their efficiency. Factories in both the meat and vegetable industries are actually struggling to find skilled workers with the necessary qualifications. And these are to fill jobs such as meat cutting, packaging, and food and meat grading. Some may see that increasing the number of workers in the factory will improve efficiency, but this may have a negative effect and subsequently increase the risk of injuries in the workplace. In both the meat and vegetable pack houses, factories use sharp-edged and heavy equipment, which can cause serious injury or death if used in the wrong environment or in the hands of someone who's not professionally trained. Pack houses need to maintain employee health and safety standards in order to protect their workers. Robotic platforms are already in use for pack houses for processes such as labeling, food grading, and food packaging. As you can see in the top right of this slide, there's a Delta robot that's separating these peppers into colors. So these are already in the industry. But in the meat industry, robots are really beginning to enter the workplace. Cutting, deboning, and shredding tasks are originally done by hand for meats like poultry, pork, and beef. However, companies such as Fanuc and ABB offer robotic automated solutions for these tasks. Implementation of these autonomous platforms into pack house processes gains major advantages, such as decreased cycle times and increased throughput. This means that meat and vegetables are delivered to the end customer faster, resulting in a longer shelf life. Robotics and automation also improve health and safety by obviously keeping workers away from sharp cutting tools and other dangerous equipment that have caused injuries in the past. Collaborative robots that work with humans help increase productivity, improve health and safety, and attract skilled workers and graduates to the food processing industry. So that's a bit about livestock production and the use of robotics in pack houses. Now I really want to talk about what the future really looks like in farming in terms of robotic use. I think it should be stressed that we do not see these changes and implementations of machines happening overnight on all farms. Some of these systems that I've detailed in this presentation are out of budget for farmers. However, as this technology matures, its price will decrease, and the availability of manufacture robots with smart, cheaper components will provide a cost-effective option for these smaller businesses in less developed countries in the future. I see a future of robust and reliable systems that will be interconnected and work alongside humans in the field or in factories. I see a future where arable robots can have interchangeable tools, allowing them to perform multiple tasks, such as tillage, weeding, crop inspection, or planting, which will support production systems to meet the increasingly high demands by improving efficiency and production throughput. I see a future of a fleet of robots which can use multiple data sources and share data between platforms to work in collaboration on a single task. This means that higher priority jobs can be dealt with in unison. A future where agricultural robots can learn and develop new skill sets and understand human processes through machine learning and AI to improve their own efficiency. It should be stressed that collaboration must be safe, ensuring the utmost safety for farm workers. Robotics should be introduced firstly for simple tasks and then transition into more complex operations, improving productivity and allowing human-based jobs to move up the value chain. Supervisory systems need to be in place in order to monitor human and robotic interactions and adjust robotic behavior if there's an unsafe situation. The system could manually take over the robotic platform by slowing its movements to completely stopping its operation. However, although this approach will slow down the productivity of the farm, development is currently in place for robots to recognize unsafe situations and adapt to the situation, maintaining productivity and workplace safety. The long-term aim for this would be for robots to replicate the interactions that occur when multiple humans are working on the same task. I see this all as a long-term aim, and this can be achieved with ongoing research and development on technologies and hardware, as well as liaising with end users in all areas of the globe to understand the way they operate throughout the growing season. One of the main advantages of interconnected robots is that they can be built at low cost using lightweight components. Many robots that are in development in crop scouting and crop weeding use 3D printed parts which can be easily manufactured on demand, either at the manufacturer or even having a 3D printer located on site. Also, using interconnected robots in a fleet allows for tasks to be spread over different robotic platforms, which reduces damage to the soil or standard crops, which could have been caused by previous heavy machinery. As I finish this presentation, I'd like to comment on a common question that I get asked, being in this industry, and the question is, are robots actually going to take our jobs away? And the answer is that robots are not going to take jobs away. They're just merely going to change the jobs that exist. Robots need people for monitoring and supervision. The more robots we need, the more people we need to build those robots. And by training your employees to work with robots, you're giving them a reason to stay motivated in their position with your company. They'll be there for advancements, and they will have unique opportunities to develop a new set of engineering-related skills. One thing that needs to be considered is that one of the industries that has seen the greatest disruption of robotics and AI has been medicine. We now have robotic and AI tools that can perform amazingly accurate diagnostics and precise surgery. But the question is have we lost doctors to this technology? And the answer is no. Doctors have simply learned to leverage the new technology and provide better healthcare. Those entering the workforce today will have to be adaptable. They have to be hungry for knowledge and committed to continuing education. What robots can actually do is make humans more productive than ever before. Workers will need to develop technical skills and keep those skills updated as technology moves forward. So yeah, that concludes actually our presentation. So I'd like to say thank you for listening. Thank you for listening. And if you have any questions after this presentation, my email's in the bottom right here, and feel free to message me or email me, and hopefully I can get back to you. Thank you.
Great. Thank you very much, Sam and Martin. That was a fantastic presentation. Well done. And it was really inspiring. I love the way that you, towards the end, you're saying you can see a future that has this and a future that has that. And you're both working on cutting edge technologies, and you're creating the future. And it's very positive. And you're considering so many different variables and opportunities. Yeah, absolutely brilliant. Thank you. And well done for the screen sharing, because we worked this out just before that the screen sharing, you have to screen share in a different way if you're doing the videos. So Sam flawlessly just interrupted his screen share, changed the settings and set the videos going. The videos worked out really well as well.
Oh, brilliant. That's good to hear.
Yeah, so everything was really good. Thank you.
Nice.
As I mentioned, this will be recorded on YouTube. Well, it is being recorded and it will be put onto YouTube. Probably takes about a week to go on there. And I was, there might be a possibility of, well, I was going to ask you if we could share slides some way, or some of those slides.
Sure.
A PDF of them. So that's great. Thank you very much for that. And I'll give you an email about sharing the slides. And what we will do is we'll put them on the IET website underneath where the event is. So you can find the event from our website, and there'll be a link to the slides there. So that'll be absolutely great. So a few people are coming and going, and that's great. A lot of people have to go. We've still got a fair good number of people here. We had about 150. And it's a few people have had to leave. It's 112 still, so we're doing pretty well. A few questions. So are you both okay just to hang around for 10 minutes?
Yeah, no problem. Yeah.
No problem.
So one of the big questions that keeps coming up, actually, quite a few questions here. I'm just going to take a random few though, is about rural crime and protecting your robot. People are stealing quad bikes and tractors. Now your robot looked quite light, really. So I'm kind of thinking, if I know where it is, I might be able to just go along with my mates and lift it. So what's stopping me doing that?
There won't be any use of the robot if you do take it. I think that's the difference. If you've got, and this has happened next to us, I live next to a farm, they've stolen 2 quad bikes and a plough. But that's because you can easily take those machines and use them off the farm. And that's not the case with robotics. As Sam would say, they're connected to the system, so you know exactly where they are. And once you've taken them, they are programmed in a way that you can't use them once you have taken them. So there's no residual value in them if you take them off the farm.
Useless. It'll just be like trying to steal something, but it's not going to work. There's no GPS RTK working. It won't have the route map.
Yeah.
Just have to sell it for scrap then, would we?
Yeah, that'd be your only alternative. Yeah.
I think the other thing as well is that a lot of people think these robots are actually working on the field on their own. They're actually there to be monitored all the time. And as Sam said, you can tell when somebody's got close to it. So the farm will be alerted as soon as there's somebody walking around the robot, and they can then have a look. There's no reason why, as robots develop, you can't put a camera on top so people can see who's near their equipment. And it's,
I think what we're heading towards here is we're not, I think what you're saying is we're not going to have a purely robotic farm. There'll always be people involved. As Samuel said, that we're not taking jobs with robots, but there will be people in the loop. There'll be people in the fields around working with the robots. So it's not as if it's just going to be a process.
correct. Yeah, that's absolutely right. Yeah.
Okay. Another question that came through is about weather. So particularly, I can imagine heavy rain, etc. So do the weather and the ground conditions limit the robots in any way? So since you don't have an operator who can adjust, you know, the control of the robot and its path depending on the weather and puddles and really boggy bits of ground, have you thought about that in any way?
Yeah, so I mean, with any machinery in a field, if you're in serious boggy conditions, I think they're all going to suffer. But with our robots, we monitor performance and through speed and power through its electrical motors. So it itself, it analyzes its performance, and in a case if it's really boggy situation, then you know you may have to stop. But that's the thing. It's able to understand the situation and recognize if it's not worth scouting. So yeah, that's really how our system works in terms of in harsh conditions.
Okay. And what about digging up root crops, because that's going to take quite a lot of energy as well? Have you got any plans for root crops?
Right. I think there's two different types of harvest. There's a slaughter harvest, which is your carrots, potatoes. There's very much at the moment, I think, as Sam said in his presentation, that the farm industry is not going to suddenly go from fully driven machinery to autonomous vehicles overnight. Certainly for root crops, there's already seen that there's plenty of machinery out there on the market which can cope with the harvest at the speed. I think where the development is going to be coming to is selective harvesting. So crops that are very delicate, like lettuce, or crops that require selective harvesting, like broccoli. There's certainly a lot of development going on right now to develop machinery for those types of crops. But that has its benefits as well. By using the scouting with that technology, the farmer can then target where he actually harvests the crop. So it might be that we might not completely autonomize the whole harvesting system, but certainly by using the scouting system, you can then target different teams in different areas of the farm, depending on where you think you need to go to actually harvest to get the most amount of yield off that crop. Right now, if you say plant 100 hectares, probably only about 50% of that crop actually comes to fruition. By using robotic technology, you can increase that yield dramatically and then hopefully get more yield off the same land, or even reduce the amount of land being used for crop. But yeah, certainly in the next few years, this is the big area of development at the moment, is developing machinery for selective harvesting of various crops around the world. And that is coming.
And another question, which is kind of along the same lines, is in the future, do you think that crops will be developed to make technology easier to use?
It is, that's definitely the case now. There's already varieties of broccoli being grown. They grow much higher off the ground, which make them easier to harvest via robotic means. Certainly, if you look at some of the old varieties like Parthenon, which are very, very close to the ground, they're quite hard to harvest because they're very close to the ground. They get affected by dirt and muck getting onto them, which means that if you want to use heavy machinery over the top of them, it makes it easier to damage them. And obviously, as you know, crops like that, they're pretty worthless if they're covered in mud. Where there's new varieties, especially in the States, which are nearly 4 feet high, which makes it a lot easier to harvest. So there's a lot of technology and a lot of new varieties of crop going into that to allow it to make it easier for machinery to harvest them.
And I think they've been training fruit bushes to grow flat as well, so along fences, So
Yeah,
it's
well, that's not actually new. If you go, I've actually been to a heritage site and a Victorian orchard where that's exactly how they grow the crop. This is not a new technology. I think they call that a 2D farm, where they effectively have apple trees growing along fences, so that the apples are presented to the robotic harvesting only in one dimension. But that's not a new invention. If there's a particular stately house you can go to in Wales, we went to a few weeks ago, and that's exactly what they've got. And those trees have been planted over 100 years ago. So
Victorians really were forward thinking, weren't they? They knew robots were coming.
Well, if your as I have done in my own garden, if your trees are 25 foot high, it makes it very hard to actually harvest the apples off the top of them. But if you train them to grow a lot lower, it makes it a lot easier. So obviously, training the trees along a fence makes it a lot easier for a robot to pick them. That's exactly what they are doing now.
So what about the costs of all of this as well? Is it cost effective to have, well, will it be cost? I know it's still research at times now, but will it be a big factor?
Yes, definitely. One of the areas we're looking at is the whole cost of system. I think one of the areas that sometimes is not being looked at in robotics is the whole process as a whole. Many people have looked at harvesting crops, and they're literally just looking at the actual the process of picking the crop, the actual harvest part of it. What they're not looking at is the entire crop cycle, in terms of the entire cost for that crop cycle, and certainly looking at the cost of the machinery and how long that takes to pay back, and also the speed of harvest as well. In order to get farmers to buy into the systems that we're designing, we have to make sure that whatever we design fits in with the process they want it to fit into. We can't go and drag them in a completely different route. They're not going to want to invest hundreds of thousands of pounds in a system that only solves part of their problem. We've got to have a look at the whole process, not just just one small part of it.
Okay. Wonderful. Okay, well, I'm going to bring it to a close there, because I'm aware of the time, and you have been going for about an hour and a half now. I'm just going to stop the recording, so I'll do that.